Every time you click Create Instance in a cloud console, you're making a promise you can't track. Think about it. You log into AWS, click through 5 screens to launch a virtual machine, configure a security group in another tab, set up a database in yet another. And now your entire production infrastructure exists only as a series of clicks that nobody documented. Want to recreate this in a staging environment? Good luck remembering every setting. Want to review changes before they go live? There's no diff for mouse clicks. And when something breaks at 2 a.m., you're scrolling through console histories trying to figure out what changed. This is the problem that infrastructure as code was built to solve. And the tool that defined this space is Terraform. What if you could describe your entire infrastructure in a text file, review every change before it happens, and reproduce everything with a single command? That's exactly what Terraform does. But the real magic isn't the config files. It's the invisible machinery working behind the scenes. Let's open the hood. Terraform uses its own configuration language called HCL, which stands for HashiCorp Configuration Language. And the key idea is simple. You describe what you want, not how to create it. Here's what that looks like. You write the word resource, followed by the type like Oz_instance, then a name you choose like web. Inside the braces, you list properties, the AMI, which is the machine image, the instance type like T3.micro, and that's it. This block tells Terraform, I want an EC2 instance with these properties to exist. Notice what's missing. There's no step 1, call this API. No step 2, wait for response. You're not writing a script, you're writing a declaration. This is the difference between imperative and declarative. An imperative script says do this, then this, then this. A declarative config says, here's what the end result should look like. Terraform figures out the steps. This distinction matters because it means Terraform can compare what you want to what you have and compute the difference. That's the foundation everything else builds on. Here's a question. Terraform can manage Oz resources, Google Cloud resources, Azure resources, databases, DNS records, even GitHub repositories. How does one tool know the API of every service on the internet? The answer is, it doesn't. Terraform itself is just a core engine. The actual knowledge of how to talk to Oz or GCP or any other service lives in plugins called providers. When you write a resource block with the type Oz_instance, Terraform knows it needs the Oz provider. When you run Terraform init, it downloads that provider plugin automatically. The provider is what translates your HCL declaration into the actual API call that AWS expects. Think of it like a universal remote control. The remote, Terraform core, has a standard interface, but each device, each cloud provider, needs its own translator module. The AWS provider knows the AWS API. The Google provider knows the GCP API, and there are over 3,000 providers available. This plugin architecture is what makes Terraform truly universal. You write the same style of configuration regardless of which cloud or service you're targeting. Now here's the piece most people miss, and it's arguably the most important part of Terraform. After Terraform creates a resource, it needs to remember that it did so. Otherwise, the next time you run Terraform, it would try to create everything all over again. This is where the state file comes in. Terraform stores a file called terraform.tfstate. It's a JSON document that maps every resource in your configuration to its real-world identifier. Your Oz_instance.web resource maps to an actual EC2 instance with the ID I-ABC123. This mapping is critical. It's how Terraform knows the difference between this resource needs to be created and this resource already exists and just needs to be updated. But here's the danger. If the state file gets out of sync with reality, things break. Someone deletes a resource manually through the console. The state file still thinks it exists. Terraform will get confused on the next run. The state file is Terraform's memory, and like any memory, it needs to stay accurate. Lose it, and Terraform forgets what it built. Before Terraform creates or changes anything, it does something clever. It analyzes your entire configuration and builds a dependency graph. Let's say your config defines a VPC, a subnet inside that VPC, a security group, and an EC2 instance that uses both the subnet and the security group. Terraform reads these references and constructs a directed acyclic graph, or DAG, where each edge represents a dependency. The VPC must exist before the subnet. The subnet and security group must exist before the EC2 instance. But notice, the subnet and the security group don't depend on each other. They can be created in parallel. This is the power of the dependency graph. It gives Terraform two things. First, a safe ordering. Resources are created from the roots of the graph downward, ensuring no resource is created before its dependencies. Second, parallelism. Independent branches of the graph can execute simultaneously, making operations faster. And when you're destroying infrastructure, the graph reverses. The instance goes first, then the subnet and security group, and finally the VPC. Leaves before roots. Same graph, opposite direction. Now we have all the ingredients. HCL describes what you want. The state file records what exists. The dependency graph defines the order. Terraform Plan brings them all together. When you run Terraform Plan, Terraform does three things. First, it reads your configuration files. Second, it reads the state file. Third, it queries the actual cloud infrastructure to check for any drift. Then it computes a diff. Just like a Git diff shows you what changed in your code, Terraform Plan shows you what will change in your infrastructure. Green plus signs mean this resource will be created. Yellow tildes mean this resource will be modified. Red minus signs mean this resource will be destroyed. And here's the crucial part. Nothing has actually changed yet. Plan is a preview, a dry run. You read the output, verify it makes sense, and decide whether to proceed. Caught a mistake? Fix your config and replan. This review step is what makes Terraform safe for production. No surprises, no accidental deletions. You always see the change before it happens. You've reviewed the plan, everything looks good. You type Terraform apply and confirm with yes. Now Terraform gets to work. It walks the dependency graph from the roots outward. First, it creates the VPC and calls the AWS API. It waits until Oz confirms the VPC is ready. Then it moves to the next level, creating the subnet and security group in parallel. Once those are confirmed, it finally creates the EC2 instance. As each resource is successfully created, Terraform immediately writes its real-world ID back to the state file. This is important. If something fails halfway through, say the EC2 instance creation hits a quota limit, the state file already has the VPC, subnet, and security group recorded. You fix the quota issue and run apply again. Terraform reads the state, sees what's already done, and picks up right where it left off. Only the EC2 instance gets created this time. This resilience is by design. Terraform treats every apply as idempotent. Run it once, run it 10 times. If the desired state matches reality, nothing happens. Only the differences get applied. Not all changes are created equal. When you modify a resource in your config, Terraform has to decide, can this change be applied in place, or does the resource need to be completely replaced? Some changes are simple updates. Want to add a tag to your EC2 instance? That's an in-place modification. The instance keeps running, and Terraform just calls the API to update the tag. But some changes are destructive. Want to change the AMI, the machine image? Oz can't swap the image on a running instance. Terraform must destroy the old instance and create a new one. This is called a force replacement. Terraform knows which changes require replacement because each provider defines it in the resource schema. When you see forces replacement in your plan output, pay attention. Your resource will be destroyed and recreated. There's also a manual override. The Terraform taint command marks a resource as damaged, forcing Terraform to replace it on the next apply. This is useful when a resource is in a broken state that Terraform can't detect automatically. Maybe a server is running, but the application crashed during provisioning. Taint it, apply, and Terraform rebuilds it from scratch. Everything we've discussed works great for a single developer. But what happens when a team of 5 engineers all need to manage the same infrastructure? If the state file lives on your laptop, nobody else can see it. 2 people might run apply at the same time with different versions of the state, and now your infrastructure is in an inconsistent mess. The solution is remote state backends. Instead of storing Terraform.tf state locally, you configure Terraform to store it in a shared location, like an S3 bucket. Now everyone reads from and writes to the same state. But there's still a race condition. What if 2 engineers run apply simultaneously? They'd both read the same state, compute their plans, and try to apply conflicting changes. This is where state locking comes in. When you configure a DynamoDB table alongside your S3 backend, Terraform acquires a lock before any write operation. The first engineer to run apply gets the lock. The second engineer sees a message: state is locked. They have to wait until the first operation completes and releases the lock. Lock, apply, unlock. It's simple, and it prevents corruption. Let's take a step back and see the full picture. Terraform takes a powerful idea, describe what you want, and let the tool figure out how to get there, and makes it work across any cloud, any service, at any scale. Your HCL configuration declares the desired state. Providers translate that into API calls for hundreds of services. The state file tracks what actually exists in the real world. The dependency graph ensures operations happen in the right order and in parallel where possible. And the plan-apply cycle gives you a review step before anything changes. In practice, teams take this further. They write reusable modules, shared configurations that standardize how resources are created across the organization. They use workspaces to manage separate environments like dev, staging, and production from the same codebase. And they integrate Terraform into CI/CD pipelines, where every pull request triggers a plan, and merging to main triggers an apply. What started as a tool for provisioning virtual machines has become the backbone of modern infrastructure management. And now, you understand the machinery that makes it all work. Thanks for watching.